Hello everybody, welcome to this game development tutorial in C++. In the past tutorials, we have created a pawn game from scratch, and today we're going to finish the game by adding a menu and some final polish. This is what we have so far. Pretty cool, right? So make sure you are up to date with the series by watching the previous episodes on YouTube. Let's get started. First of all, let's make a menu for the game, where the user will be able to select whether he wants to play against the AI or against another player. As you can see here, most of this code will only run if you are in the actual gameplay, not in the menu. So we're going to have to separate this code. I'll create an enum that will tell us what the current game mode is, menu or gameplay. So if you are in the gameplay, we'll continue what we are already doing. So I'll do the player input and the simulation, ball simulation, data rendering. But if we're in the menu, I'll just draw a rectangle for now. Awesome! Before we take our time to draw some useful stuff, I'll just make the actual functionality for the menu. We'll have two buttons, one for the single player mode and one for the two player mode. I'll make a hot button variable that stores which button, 0 for single player and 1 for two player, I have selected. It's the same idea for the enum. And since we only have two buttons, we can make this code really simple and just do an if on the hot button. If the left button is selected, I'll make it of a different color, and the same thing for the right button. Okay, now let's make a way to change the hot button. If you press the right or the left key, we'll just invert the value of the hot button. You can imagine that making more buttons here would involve actually incrementing the value of the variable and wrapping that around to 0 if it tries to go over the number of buttons we have. We're going to have to add the left and the right buttons to our input system. Yeah. To make the enter actually starts the game super easy. If I press the enter button, I'll change the current game mode and set whether or not the enemy is an AI based on the hot button. I will create a variable for that now. And remember the pound if we added last tutorial? We'll change that to an actual if, because the player can choose whether he'll control the enemy or not. Let's see. Oh, we don't have the enter button. Let's add that really quickly. Okay, this is single player. And this is multiplayer. Perfect! So in terms of functionality, our menu is complete. But we have to make it look better, right? And if you remember from the previous tutorials, our rendering can only draw numbers. Now maybe this is the time to actually implement a font in our engine so we can draw any text, but I'll leave that to the next tutorial series. Now, we'll just double down on the hacky rectangle-based solution and do the same thing we did for the numbers with the letters. But as you can imagine, it can take a while to specify them in the same way we're doing for the numbers. So we'll improve the system a bit. What I want to do is to specify which rectangles will be filled for a given letter in a tile map kind of way, like this. That'll be much easier, right? So let's make a table with this data. But how do we read this data? Well, it's just a 2D array of strings. So we can expect the letter A to be in the array's first position, like this. And since each letter is an array of its own with several rows, we can store it as a pointer to a character pointer, a string. Let's see that in the debugger to understand it better. As you can see here, the table has only one letter at the position 0, and this letter has several rows. So for each letter we'll draw, we have to go through each row, and for each row, we have to see if there's a 0, which means to draw a rectangle, or a space, which means skip. Let's write the code now. The function will receive a size, a position, and a color, like our draw number function. It'll also take a text, but one step at a time for now. So we have the letter A here. We'll go through each row, and we know there are 7 rows, right? And while we have a valid character in the row, we'll see if it's 0. If it is, we'll draw the rectangle at the desired position and move the X position an entire size. After drawing the row, I'll move the Y position and set the X position to the original X every time one row is drawn. Let's not forget to increment the row pointer so it points to the next character in the row. Great, there's our letter. Let me review what we did, in case it wasn't 100% clear. We have a letter table, which is a 2D array of strings. Remember that a string in C is represented as a pointer to a character. We grab a letter and run through each row, so it starts pointing to the first row's first character. If it's 0, we draw it. We also move the X position and the row pointer, so we are ready to draw the next character. And when the row is finished, we reset the X to its original position so we can start drawing the next row and move the Y position down. And we do this for every row. Let me know if you understood that in the comments below. All I have to do is receive a string or a character pointer and run through each character. But how do you know what letter corresponds to in our table? Assuming the letter A starts in our table at the position 0, how do you map the A that the C string gave us with our desired index? Now let's take some time now to talk about character encoding, because it's a very important topic, especially if you want our game to be localized in different languages. The most basic character encoding we'll see around is the ANSI encoding. It stores each character in 1 byte, or char, according to the ASCII table. If you take a look at the ASCII table, we'll see what number, both in decimal and in hex, each character maps to in this encoding. C and C++ uses this encoding as a default string. The advantage is that it's really easy to deal with because each character is only 1 byte, and we can test their value really easily. However, there's a problem. We can't map every possible character in a single byte, or 256 values. So we need more space for the full Latin alphabet, for the Russian, the Chinese, the Japanese, the Arabic, and all other non-Latin based alphabets. Every possible character is specified in a Unicode character table. It starts off just like the ASCII table, but it quickly gets all sorts of different characters and alphabets. But how are we supposed to encode all those possible characters? Well, the first solution was just to store them as 32-bit integers. That's the UTF-32 format. But we are wasting several bytes per character, especially considering that we don't use the full 4 bytes most of the time. So there's a more common way to encode Unicode table, is with the UTF-16 protocol, which is the same thing, but we store them as a 16-bit integer. Windows uses a similar 16 per char standard in its API, along with the ASCII encoding, and Windows called it wide characters, because it's larger than a single char type. And while UTF-16 is better than UTF-32, it still has its share of problems. For once, we are still using more than 1 byte than we need most of the time, and we will have to keep mapping from ANSI to UTF-16 all the time. Enter UTF-8. In this encoding, characters are of a variable width, so they can appear as 1, 2, 3, and even 4 bytes. The single byte characters map perfectly to the ASCII table, so no need to do any conversion, and we use as little space as we need to get a full Unicode table in our strings. Like I said, standard C and C++ encoding for literal strings is ANSI by default, so using a single byte per character. In modern versions of C++, we have the capability of setting the encoder by adding a prefix to our strings, like U8 for UTF-8, lowercase u for 16-bit Unicode, uppercase L for wide characters, uppercase U for 32-bit Unicode. So if you want to build a robust text system, along with a localization system to efficiently support multiple languages, you will want to carefully consider the encodings and their transformations. I hope you like this introduction to character encoding. Let's continue with our game. Now that you know that this string will come as a Nancy encoded string, we can just pull up an ASCII table to see what the uppercase letters map to, for instance. The uppercase A is 65 in decimal, perfect. So if you want A to map to 0 and B to 1 and so on, we can just subtract 65 to the character. Or the letter A, which is 65. Let's not forget to move to the next letter as well, and move the X position to give some space in between the letters. And make sure the original X is being set to the new X as well. The Y position also needs to be reset for the new letter. Now let's add more characters to the table and test drawing some text. Awesome! We have our text rendering system. Now, one simple way to improve the system is to have another table that contains the kerning information for each character. That is, how much we should move. Because in uppercase H takes more horizontal room than in lowercase I, for instance, in most fonts, we should not always move the same amount, 6 in this case, but a specific amount per character. But I'll leave that for you to play with. The only thing left is the space character, which is the decimal 32. We'll hard-code it for now to just skip one character. So let's try adding our actual menu text. Awesome! Now the game title and information. We're going to have to add the slash and the dark character to our table. I'll hardcode them as well. That's it, that's our menu. Now the game is mostly done. There are just a few improvements left to do. Like, let's change the window title to our game title. Pretty easily, right? Let's also make sure we are on the release build, because that's the one we're going to distribute to the players. And now let's hide the mouse cursor. It's as simple as calling the show cursor function with a false parameter. Now whenever the cursor is inside our window, it will be hidden. Another thing is to make the game full screen. That's what players expect, right? Now it's kind of finicky to make the window full screen. So firstly, we're going to have to make sure our window has the overlap flag set to false. So I'm going to put this tilde here, which is like to negate this flag. Then we'll get the player's monitor info. Set the window to be on top with the monitor size as the new width and height. As well as setting the no owner Z order and the frame changed flags. You can learn more about those functions on MSDN. Wow, it's so awesome to play the game full screen. Now it almost looks like a real finished game, right? But I'll do one more thing before we call it done. In a bigger game, we would make use of a profiler, so we would know what parts of the game are taking the most time. So we can analyze and decide what to optimize and how. But we're not building a profiler for this game. If you want to learn more about that, you can search for a profiler on my YouTube videos. But there's an easy optimization we can do. Right at the beginning of the game loop, we clear the screen with a color, pixel by pixel, and then draw a giant rectangle the arena on top of most of that. That's such a waste because most of the pixels we cleared don't get seen in the first place. This is called overdraw, where you draw a single pixel multiple times unnecessarily. It's super easy to optimize this in this case. Instead of drawing the screen, then drawing the arena, we can draw the arena and then draw the 4 remaining rectangles in the borders. Now, since we are clipping the min and the max position, we could just add a giant number here and let the renderer do the clipping. But we could also make a specific rendering function that will draw starting from the first pixel, whichever that may be. So let's do that. I'll first transform the x and y values to pixel coordinates. And then just draw the 4 rectangles to cover the remaining screen space. Good. We can't actually see how many milliseconds we improved, but you can imagine that we were drawing the screen twice, pretty much, right? So 8 million pixels for a 4K display would be 16 million pixels for no reason. And now we don't have any significant overdraw. That's success. And the game's done! I really hope you enjoyed this tutorial series and that you learned a lot. Remember that practice makes perfect, so you should do your own games as well. Start off by thinking how you can make small improvements to this game to make it more interesting. Maybe have the ball increase speed with time. Maybe make the goal give more points the longer the rally lasts. If you want some inspirations for these ideas, check out this game on my itch.io page, Two-Handed Pong. In it, I play around with several mechanics changes to a normal Pong game. And certainly taking the time to design and program some mechanics will improve your skills. So that's the challenge for today. We are going to have a bonus tutorial next, because we need to publish our game as well. Even though it's a small game, publish it will improve our overall development skills and prepare ourselves for larger projects. The more games you publish, the better we'll be at actually finishing the game by having real people play it. So I'll see you next time.